Hello, the purpose of this video is to give a short introduction to the shift-left paradigm. Cybersecurity is a concern across many sectors. In November 2011, hackers were alleged to have destroyed a pump used to pipe water to thousands of homes in a US city in Illinois. They're thought to have used their access to the utilities network to break the pump by turning it on and off quickly. At the Ruxon Breakpoint Security Conference in 2012, Barnaby Jack showed how an attacker with a laptop located up to 50 feet from a victim could remotely hack a pacemaker and deliver an 830-volt shock. In November 2014, it was reported that a blast furnace at a German steel mill suffered massive damage following a cyber attack on the plant's network. Attackers were said to have used booby-trapped emails to steal logins that gave them access to the mill control system. This led to parts of the plant failing and meant that a blast furnace could not be shut down as normal. In 2015, it was reported that Chris Valasek and Charlie Miller had managed to hack into a Jeep car, showing that it was not necessary to physically access a car to compromise its security. And in November 2016, San Francisco's public transit riders got what seemed like a Black Friday surprise. The system wouldn't take their money. Someone had attacked the system and was demanding a ransom. Cybersecurity is primarily concerned with the protection of data. However, in developing a secure application, it is easy to forget that providing such protection involves more than just the data itself. It also demands that the system is designed to safeguard that data against aggressors and to defend interfaces to the system. Traditional practice for secure code verification is largely reactive, meaning that code is developed in accordance with relatively loose guidelines and then tested by means of performance, penetration, load, and functional testing to identify vulnerabilities prior to their being addressed. A better proactive approach is to ensure the code is secure by design. That implies a systemic development process where the code is written in accordance with secure coding standards, is traceable to security requirements, and is tested to demonstrate compliance with those requirements. The term shift left is most often heard with reference to continuous development processes typified by DevSecOps. This website offers a very good explanation as to why it has come to the fore. Quoting from the website, security was merely wrapped around the outside of the application prior to release to end users, and this step necessarily added time. Additionally, a tighter integration of security through the process leads to better security outcomes versus tacking it on at the end. That's a fine principle in theory, but what does it mean in practice? Security requirements represent a pivotal component in the shift-left principle. But it's no good having requirements if the software you develop doesn't fulfill them. In the DevSecOps model, shifting left is achieved by superimposing security-related activities onto the DevOps principles throughout the continuous development process. Requirements traceability is maintained for each development iteration, as illustrated by the orange arrows. Although the term shift left has gained prominence in DevSecOps circles, the idea of establishing requirements early and adhering to them has also long been established in functional safety software development. For example, this is a V model representing the EN5012X lifecycle model for railways and other guided transport systems. As the diagram shows, requirements are established and traced here too, but in this case they are functional safety requirements. No surprise then that verification and validation processes associated with a shift-left V model for secure software development are largely analogous and complementary to the processes usually associated with functional safety application development. To ensure smooth project development, all parts of the product and the process of its development must be understood by every team member in the same way. Clearly defined functional and security requirements help ensure that this is the case. This is not to say that software can never be used as an intellectual modeling clay to create a proof of concept, but the ultimate result of such experimentation should be clearly defined requirements and production code appropriately developed to fulfill them. There is little point in having requirements unless they are fully and completely implemented. That can be established by means of traceability. Bidirectional traceability means that traceable paths are maintained both forwards and backwards. Forward traceability demonstrates that all requirements are reflected at each stage of the development process, including implementation and test. The impact of any changes to requirements or of failed test cases can be assessed by applying impact analysis, which can then be addressed. The resulting implementation can then be retested to prevent evidence of continued adherence to the principles of bidirectional traceability. Equally important is backward traceability, which highlights code that fulfills none of the specified requirements. Oversight, faulty logic, feature creep, and the insertion of malicious backdoor methods can all introduce security vulnerabilities or errors. Standards have an important part to play in the application of shift-left principles. There are a number of secure coding standards available to choose from. For example, CERT C++ is a coding standard designed for the development of safe, reliable, and secure systems that adopts an application-centric approach to the detection of issues. MISRA C 2012 offers another option, despite a common misconception that it is designed just for safety-related, not security-related projects. Static analysis tools vary in terms of their ability to identify the more subtle nuances of standard violations, but the more sophisticated implementations can seem slower because of the additional processing required to achieve that. A sensible approach is to choose tools with the option to run in lightweight mode initially and to provide a more complete analysis as development progresses. Almost without exception, these secure coding standards are recommended for use by the broader security-focused process standards. In safety-critical sectors, such standards frequently complement those focused on functional safety. For example, J3061, Cybersecurity Guidebook for Cyber Physical Vehicle Systems, which is soon to be superseded by ISO SAE 21434, complements the automotive ISO 26262 functional safety standard, and automated development tools can be integrated into development workflows for security critical systems and can also accommodate functional safety demands concurrently. IEC 62443 is a series of multi-industry standards defining cybersecurity protection methods and techniques. These are categorized to apply to all stakeholders, including manufacturers, asset owners, and suppliers. The fourth in the series, IEC 624434, specifies the requirements for the secure development of systems used in industrial control and automation. It is also frequently applied in the world of guided transport systems. The principle of testing early and often demands the use of a different type of tool to those traditionally associated with security testing. Whatever the preferred model, testing early and often is paramount if security is to be developed in, not added on. Testing early and often becomes a much more practical proposition if that test is seamless and an automated part of the process. We already touched on the application of static analysis, but dynamic analysis is every bit as important. This diagram shows the process to be used in creating unit tests that will demonstrate the fulfillment of requirements. But it is also possible to use the same tools to demonstrate the robustness of the code base by automatically generating taxing tests to exercise typical vulnerabilities in code, such as those associated with boundary conditions. And finally, traditional security tests such as fuzz and penetration tests remain a vital component in the world of shift left. But here they are used to confirm that the security you have designed and developed into your code base is effective, rather than to expose issues for you to address. I hope that has given you a useful insight into the shift left paradigm and what it means for the development of secure embedded application code. If you have any questions, please do contact us.